everyone, my name is Drutilekha Adhikari, a student of Mathabhanga College, Chemistry Department, 3rd year. Today I am going to discuss about the cycloaddition reaction. Cycloaddition reaction may be defined as the pericyclic processes involving the formation of a ring through the formation of two new sigma bond at the terminal of the pi system by concerted combination of two or more independent pi systems. The reverse process is called cycloreversion or is referred to as a retroreaction. Here we are taking a 4 pi electronic system and a 2 pi electron system, and those will go cycloaddition reaction and we will get a product that is having 2 pi electrons. Classification of cycloaddition reactions. Based on the number of pi electrons of the reacting species involved in the reaction, cycloaddition reaction have been classified as 2 plus 2 cycloaddition reaction, 4 plus 2 cycloaddition reaction, 6 plus 2 cycloaddition reaction, 4 plus 4 cycloaddition reaction, 8 plus 2 cycloaddition reaction, and 6 plus 4 cycloaddition reaction. There are several classifications of cycloaddition reaction. First one is the dimerization of ethylene, second one is the Diastellar reaction, third one is the cycloaddition of allyl cation to Dyne, fourth one is 1,3-dipolar cycloaddition reaction, and fifth one is 2 plus 2 plus 2 cycloaddition reaction. Now we will discuss about superficial bond formation. Bonding interaction between the lobes on the same face of one reactant and the lobes on the same face of the other is called superficial bond formation. That is, for the cycloaddition reaction to occur, HOMO of one reactant interacts with the LUMO of other. Positive terminal lobe of one can interact with the positive terminal lobe of other, and the negative terminal lobe of one can interact with the negative terminal lobe of other. If the structure of HOMO and LUMO of the two reactants is such that bonding interaction occurs between the lobes on the same face of one reactant and the lobes on the same face of other, then the interaction is called superficial interaction. Another one is interfacial bond formation. Bonding interaction between the lobes on the same face of one reactant and the lobes on the opposite faces of the other is called interfacial bond formation. That is, if the structure of HOMO and LUMO of the two reactants is such that bonding interaction occurs between the lobes of the same face of one reactant and the lobes of the opposite faces of the other, then the interaction is called interfacial interaction. Now let us derive the Woodward-Hoffmann selection rule for 2 plus 2 cycloaddition reaction. We will discuss 2 plus 2 cycloaddition under thermal condition. In ethylene, there are 2 pi molecular orbitals Ψ1 and Ψ2. Under thermal condition, Ψ1 is fully occupied by 2 pi electrons and Ψ2 is fully vacant. So Ψ1 acts as HOMO while Ψ2 acts as LUMO. During cycloaddition, HOMO of one ethylene molecule combined with the LUMO of other. Since LUMO and HOMO have two different symmetries, so the allowed bonding interaction will be interfacial, which is not possible in small ring system like cyclobutane. So 2 plus 2 cycloaddition is thermally not allowed. Here we are discussing 2 plus 2 cycloaddition under photochemical condition. Under photochemical condition, one of the 2 pi electrons from Ψ1 jumps to Ψ2, making Ψ2 as HOMO. Symmetry of HOMO of excited molecule and LUMO of ground state molecule are the same. So the allowed bonding interaction will be supraspecial. That will allow the formation of cyclobutane ring. So 2 plus 2 cycloaddition is photochemically allowed. Woodward-Hoffmann rule for 4 plus 2 cycloaddition reaction. Four plus 2 cycloaddition reaction in thermal condition. In 4 plus 2 cycloaddition, under thermal condition, Ψ2 and Ψ3 of 1,3-butadiene are HOMO and LUMO respectively. In ethylene, Ψ1 is HOMO and Ψ2 is LUMO. If we look at the structure of HOMO and LUMO of 1,3-butadiene and ethylene, we will find that HOMO of one and LUMO of other have the same symmetry. Thus, HOMO of 1,3-butadiene can combine with the LUMO of ethylene, and HOMO of ethylene can combine with the LUMO of 1,3-butadiene in superficial fashion. But in general, interaction between HOMO of 1,3-butadiene and LUMO of ethylene is energetically more favorable because of its small energy gap between these two molecular orbitals. So 4+2 cycloaddition is thermally allowed. Now we are discussing about 4+2 cycloaddition reaction in photochemical condition. Under photochemical condition, one of the two pi electrons from Psi2 of 1,3-butadiene jumps to Psi3, making Psi3 as HOMO and Psi4 as LUMO in ethylene. Psi1 is HOMO and Psi2 is LUMO. The HOMO of butadiene and LUMO of ethylene have different symmetry, so the allowed interaction will be interfacial. So 4+2 cycloaddition is photochemically not allowed. Based on the previous discussion, we can summarize Woodward-Hoffmann rule for cycloaddition reaction in a tabulated form. If the number of pi electrons of both the reactants taking part in the reaction is 4n, that is 4, 8, 12, etc., under thermal condition, allowed mode of bond formation will be interfacial. While under photochemical condition, allowed mode of bond formation will be superficial. If the sum of a number of pi electrons of both the reactants taking part in the reaction is 4n plus 2, that is 6, 10, 14, etc., under thermal condition, allowed mode of bond formation will be superficial, and under photochemical condition, allowed mode of bond formation will be interfacial. Even though interfacial bond formation is symmetry allowed, in certain cases as shown in the table, it can occur only with the rings that have 7 and more ring atom. Now we are discuss about Diastellar reaction, which is 4+2 cycloaddition reaction, or we can say which is a type of 4+2 cycloaddition reaction. In this reaction, we have 1,3-diene reacting with an alkene known as dienophile to form a cyclohexene product, also known as an adduct product. The pi electrons between the carbon 1 and 2 move in between carbon 2 and 3. The pi electron between carbon 3 and 4 move out to form a sigma bond between carbon 4 and B. And the pi electrons between B and A move out to form a sigma bond between carbon 1 and carbon 2. Carbon 1 and carbon A. This reaction is a concerted reaction, which means all bonds are being broken and being formed at the same time. In this reaction, we have two sigma bonds being formed and one pi bonds, and we are breaking 3 pi bonds. Since we know sigma bonds are stronger than pi bonds, so the overall reaction is exothermic. The major consideration of Diastellar reaction is the conformation of the Dyne. Here we have two conformation, the S trans and the S cis, represented here in equilibrium. The Dyne more likely to be in S trans conformation because of the less steric strain. S here stands for single bond and trans stands for alkenes pointing in opposite direction. In cis conformation, S for single bond and cis stands for the alkene pointing in same direction. The Dyne must be in S-cis conformation because the proximity of the dienophile and the Dyne must be close enough in order for the reaction to take place. S-cis undergoes Diastellar reaction, whereas S-trans does not. Reactivity of Dynes in Diastellar reaction. Factor enhancing reactivity of Dyne. ability of Dyne to adopt an S-cis conformation, planarity of the system, electron donor group. Any factor that favors S-cis conformation increases the reactivity of Dyne towards Diastellar reaction, while any factor that favors S-trans conformation decreases the reactivity of Dyne towards Diastellar reaction. The reactivity of 1, 2 and 3 is higher towards Diastellar reaction with malic anhydride than 4, 5 and 6 because in 1, 2 and 3 the Dyne is locked in S-cis conformation. Compound 7 is more reactive than compound 8 because in compound 8 S-cis conformation is less favored. Due to the steric strain. Compound 9 and 5 have higher reactivity than compound 6 due to the presence of electron donating group. Also presence of these groups disfavored S-trans conformation and favor S-cis conformation. Compound 9 is more reactive than compound 5 because in compound 9 due to bulky tertiary butyl groups, S-trans is not favored and S-cis is more favored. Reactivity of dienophiles in Diastellar reaction. Factors affecting or enhancing reactivity of dienophiles are electron withdrawing groups, a weak pi bond and release of ring strain. Here you can see the more the electron deficiency in dienophile, higher is the reactivity. Now we will learn the stereochemistry of the Diastellar reaction. Relative orientation of groups in the dienophile remains unchanged during the course of Diastellar reaction. This means two groups which are cis in the dienophile will remain cis, while those which are trans remain trans in the Diastellar product. As you can see, in this first product, a cis dienophile reacts with a Dyne and the product is cis product. And in the second one, a trans dienophile reacts with a Dyne and the product is trans product. Let's take the example of 1-methoxy-1,3-butadiene with methyl acrylate. After Diastellar reaction, the skeleton of the product will look like this. Let's take another example in which cyclopentadiene reacts with ethyl acrylate to produce Diastellar adapt. In this case, the outer group of the Dyne are hydrogen atoms. So the Diastellar reaction will give an endo product in which hydrogen and the ester group will be cis, and an exo product in which the hydrogen and the ester group will be trans to each other. Thank you for watching this video.